back. We're now going to talk about convex functions. We spent some time talking about convex sets. Convex functions are the other part of the equation for us. Remember what we're studying here is this central object. So let's first do it by picture, just like we did with convex sets. This function is convex. And what is a defining property? If I take any 2 points, the straight line that joins them always lies above the function. Let's translate this picture into algebra. If f is a function of n variables, sometimes I'll write this as f maps Rn to R, then f is called convex if for any point x1 and x2 in Rn, for any lambda in 0, 1, remember this is lambda in 0, 1 is our way to find the line segment between 2 points, then f of lambda x1 plus 1 minus lambda x2, let's identify this in the picture. This is my point x1. This is my point x2. What is this? This is some point in this line segment between x1 and x2, and f of that is going to be whatever point is on the curve. So this tells us what the inequality is that we want. Less than or equal to lambda f of x1 plus 1 minus lambda f of x2. Anything like this is convex. What is not convex? An example of something that's not convex this. I can find 2 points. The line segment between them is actually below the function. Note that in this previous example, I didn't assume that my function is smooth. I didn't assume that it has a derivative. Didn't assume anything like that. But now let's suppose we have a derivative. We can give another definition that it turns out is equivalent. Let's go back to the picture and think about another way to characterize convex function. What else do we see? Well, for any point x, if I draw the tangent line at that point x, it is always below the function. In other words, the linear approximation at a point x always lies below the function. Let's translate that into algebra. What this says so this is my point f of x. This is the value f of y. This is saying that f of y, and let me start the same way. So f, a function f, is convex if f of y is always greater than or equal to this linear approximation. So what does it mean for f of y to be what is this point here? Well, this is the linear approximation evaluated at y. The linear approximation at x is f of x plus the gradient of f of x times y minus x. Simple as that. And again, you can see that if I don't have convexity, this is not convex by our previous definition, but you'll also note that if I pick a point and look at the, I should have drawn it a little bit better, and you look at the linear approximation at this point, it's not below the function. It's above certain parts of it. I should specify this has to be true for all y and at every point x. Okay, let's assume we have even more. So you probably remember this from when you took calculus. So back in calculus, we would take a derivative of a function, set it equal to 0, find that point, but then we knew that actually we needed to distinguish between a minimum and a maximum point. And the way we tell if we're at a minimum is if the function is like a bowl, if it's curving up. So what does that mean? It means that the derivative is increasing. Let's start with a picture. So note that at every point here, as we move, the slope of this function is increasing, increasing, increasing. What does that mean? That means that the rate of change of the slope is positive. In 1D, this means that f double prime of x is greater than or equal to 0. The rate of change of the rate of change is increasing. But in n dimensions, we need to replace the second derivative with a matrix of all the second order partial derivatives. And recall that this is called the Hessian. A function f is convex if its Hessian matrix, this is an n by n matrix, and it's a symmetric matrix, is positive semi-definite. In other words, all eigenvalues of this are greater than or equal to 0. And sometimes for shorthand, we denote that a matrix is positive semi-definite by this thing that looks like an inequality but is, well, this notation here. So here are three definitions of convexity, each requiring a different level of assumptions. In order to define this, I need a first derivative to exist and also a second derivative. Now, it turns out that one of the most useful properties, one that we're going to use again and again when we're analyzing algorithms like gradient descent, is the second property that we gave of this linear underestimate. So it's important for us to revisit this in the case where we may not have differentiability. And let's draw a non-differentiable function and see if we can generalize this idea. So I'm drawing this point here. And this is a convex function. How do we know it's convex? Well, we have our first property that doesn't require any assumptions whatsoever. Draw any 2 points, join them. The chord is always above the function. At any point here, it's a curve, so the derivative exists. I don't care about that point right now. So we can form these underestimates at every other point. But what happens over here? I'll change color so it's even more clear here. Well, it actually turns out here that we also have this property, except there's not a unique way. There's not a unique tangent to the graph. There's many, many, many different, potentially, ways to underestimate. So we have our following definition. A function is convex if for any point x, there exists some vector. I'm going to call it g to have us remember the word gradient, but it's not necessarily going to be the gradient because there's no gradient at this point. Maybe there's gradient at other points, but so there exists some vector g such that f of y is greater than or equal to f of x plus g times y minus x. All this is saying is that at every point of the function, there exists some linear function which touches the function at a point, but always lies underneath it. It doesn't have to necessarily be defined by the gradient. One thing we should note is that if f is convex and differentiable, then just according to the previous definition, g is equal to the gradient of f of x satisfies this. But moreover, it's the only g that satisfies this. It is the only such g. So the set of such g's actually, they're so important that they have a name. They're called subgradients. For a convex function, f, a vector g such that f of y is greater than or equal to f of x plus g dot product with y minus x for all y is called a subgradient. We're going to see this definition again and again and again. The set of subgradients of f at a point x is called the subdifferential. Of f at x. And it's denoted by this. So this is, in general, a set. If our function is smooth, what this note says is that there is one and only one point in the subdifferential, and that is the gradient. So this is just a way to generalize our definition 2 and generalize this definition of the gradient. Okay, let's apply these three definitions to the function, this quadratic function, x transpose qx. So f of x is equal to x transpose qx, where q is positive semi-definite. So remember, this means that q is symmetric and q has eigenvalues greater than or equal to 0. Definition 3 is really the easiest for us. We need to take the second derivative of f, and in other words the Hessian, and check whether it's positive semi-definite. But we can see right here that that of course is the case, because in this case the Hessian of f, if you remember from how do we take derivatives of quadratics, is just twice times q. And since q is positive semi-definite, twice times q is positive semi-definite, so this is indeed positive semi-definite. So we've just learned that according to definition 3, the function f of x is convex. Let's check definition 2. Remember, definition 2 tells me that I need to check that f of y, whether f of y is greater than or equal to f of x plus the gradient of f of x times y minus x, and whether this is true for all y. So the Hessian is equal to q. The gradient of f of x is just equal to twice q times x. So let's plug everything in and see how it works out. F of y on the left, I've got y transpose qy. And I need to check, so I'll keep this question mark here, whether or not this is greater than or equal to f of x, x transpose qx, plus the gradient twice qx times y minus x is greater than, is whether this relationship holds for all y. Writing it out, this is equal to y transpose qy, question mark, x transpose qx. Remember that u inner product with v is u transpose v. So this is equal to twice x transpose q transpose, but q is symmetric, so q transpose equals q times y minus x. Let's bring everything over to the left. I've got y transpose qy. I'm going to bring this term over to the left, remembering to change the sign, minus 2 x transpose q y minus x. Again, minus x transpose qx, and I'm wondering whether or not this is greater than or equal to 0. Well, with a little bit of rearranging here, we can see what happens. This is equal to y transpose qy minus 2x transpose qy. So then I've got a minus minus. So plus 2x transpose qx minus x transpose qx leaves me with a single copy of x transpose qx. And now this is equal to y minus x transpose q times y minus x. And do we need to wonder whether or not this is greater than or equal to 0? And the answer is no, we don't, because q is positive semi-definite. So that means that for any vector, v transpose qv is greater than or equal to 0, so it's certainly true for the vector y minus x. So we verified this. This indeed holds. This is a relief. The three definitions are equivalent. We knew this was going to happen. It's useful just to get used to some of these manipulations. The third one I'm going to leave for you, but I'll just set it up. So this will be an exercise. You need to check that for any x and y, and for any lambda between 0 and 1, we need to check that f of lambda x plus 1 minus lambda y is, let's think about what this inequality is so you can remember the picture, is something, some relationship, lambda times f of x plus 1 minus lambda f of y. Of course, you can just flip back and see. But what do these things represent? It's useful to make the connection between the algebra and the picture that we drew. The chord has to be above the function. And it's really the right-hand side here that's the chord. That means that this is the inequality that we're after. So you need to plug in this thing for x in the expression for f and check that this is true. Plug in and check, I'll put a question mark here, that the inequality holds. And the hint is that this is going to involve completing the square just like we had in the previous calculation. Similar calculation as above. So try this at home, and I'll see you next time.